Mold tool and die design is a very complex and specialist subject, traditionally requiring complex and specialist tools that are strong in these areas and not in others. SolidWorks addresses all these shortcomings by combining the power of a robust, fully featured 3D CAD solution with all the tools needed to take native or imported parts direct from the customer and produce fully detailed 3D inserts and mold components ready for CNC machining and with complete 2D documentation. Working with different customers requires flexibility when it comes to accepting different file formats. SolidWorks imports a variety of different 3D CAD formats, some of which are neutral formats such as IGES or STEP, and some are native CAD system formats such as ProEngineer or Unigraphics. The file format that toolmakers have been forced to work with over the years is IGES, and geometry errors are commonplace. SolidWorks automated repair tools will detect and fix most of these errors before you even see them. If we switch this off, we'll see the sorts of things that can cause problems further down the line. What we're looking for is an enclosed solid body, but here we see a surface has been created, indicating that there is a problem. So we'll just run some diagnostic tools to discover what those problems are. If we zoom into these areas, we can see some gaps which have been caused by inaccurate surface trim boundaries or surfaces missing completely. We can fix these up manually, but instead we'll just let the SolidWorks automated repair tools do the job for us. Within a few moments we get the green light and we can proceed with the design. Now the first thing we'll want to do is interrogate this design to work out how we're going to make it. SolidWorks comes with many useful tools such as a part inline check and an undercut check, certainly useful when determining if the part can be made and if we need to quote more time and cost for the job. This design has 3 undercuts, so already the price has gone up. The draft analysis will tell us if the geometry is suitable for moulding, if the pull direction is correct, and if there is enough of an angle on the walls to eject it out of the mould easily. Yellow is not a good sign. This tool is so interactive though, simply changing the draft angle or the pull direction immediately updates the graphics. We can also continue working with this graphics display on until we're satisfied that we've resolved the problems. Rather than ask the customer to make the change and wait for the new file to be resent, we can let SolidWorks make the changes for us. To add draft to the faces of imported geometry would normally be very difficult because of the fillets all around them. SolidWorks can take these fillets and remove them, automatically trimming up the surrounding geometry. Now we can treat it just as if it were native SolidWorks model and add draft and fillets as we please. As soon as the draft is applied, the yellow faces disappear, indicating that we have satisfied our design criteria. Re-adding the fillets completes the task. Finally, based on the customer's specified material, we can add a scale factor to account for the shrinkage of the material after cooling. The part inline feature will determine which faces of the model belong to the cavity and which belong to the core. By default it will take the outermost boundary, but we also need to close up any holes. The automated shutoff surface will find these holes and apply boundary conditions at the edges. If a complex shutoff face is needed, these can be made manually and used as required. The same applies to the parting surface, which will be used to separate the two halves of the mould. If the automated tools don't make the shapes you want, you can make them manually and just add them to the folders to designate what types of surfaces you have created. For example, if we take a look at the surfaces in the core side of the mould, There is a surface there that could be extended and used as a parting surface. So we'll just switch over to the surfacing tools and get to work. We can easily remove the trim boundary of the original surface and then trim it back to match the existing geometry. To save a little time, I've already created a number of sketch profiles that we'll use to complete this design. The first sketch will trim back the parting surface closer to the edges of the part, and the second will be used to define the size of the tool insert. But first we just need to drag the newly created surface into the parting surfaces folder so that when we ask SolidWorks to split the mold, it already knows what's what. Since the parting surface is smaller than the insert, we'll make an interlock surface automatically. And there we have the core and cavity of the mold. These can now be used directly for CNC machining. SolidWorks partners with best-in-class solution providers in many different disciplines, such as computer-aided manufacturing to provide the toolpaths to drive your CNC machines, plastics flow and cooling simulation to validate the mold design before it's made, or automated mold-based creation wizards to speed the design process. Whatever your requirements, there is a host of completely integrated and seamless solutions available. Since the external faces and edges of this part must not be marked, we cannot use a hot runner system to directly inject the plastic onto the top surface, nor can we feed on the outer edge, so we must feed from underneath with a subgate. Commonly used features and components can be stored in a library and reused over and over again. For this design, we'll add the sprue, runners and subgate all in one go. Just a couple of references are required to place the geometry, and now we have reused some standard mold features which we can easily modify to suit the current job if required. The undercuts on the snap fit features will need to be removed with the side core. Again, we have a sketch provided, which we just need to edit to attach it to the geometry. Turning off the shading is a quick way to seal the hidden detail. Once done, the core feature creates the side cores and the corresponding cutout in the mold core at the same time. To visualize this easier, let's just move the mold core up out of the way. Since these will be sliding in and out, we must ensure there is sufficient draft on the sides of all the sliding faces. Using regular SolidWorks features, the fine detail, which is prevalent throughout mold and die design, can be easily achieved, and since we're working entirely in 3D, we can be sure our design is accurate and works exactly as required. The other undercut feature must be made with a lifter, which we'll create from scratch. Turning off the shading again, we can see the finer detail of the hook, which we can reuse by copying the edges that we need. This will ensure that the geometry is accurate and will update automatically if a change is made to the design part. Sketch in the rest of the geometry and add some sizes. Then create the lifter using the core feature. At this time, we may also want to consider the best way to eject this part and the best locations for our ejector pins. A simple hole can be created in the core side of the mould to locate the first ejector pin. Using a sketch with points to represent the centres of all the other pins is a quick and easy way to add these features. We'll create the pins in the mould base assembly later. Finally, we may want to add some core pins for difficult to machine areas or for where extra strength is required. This is done in exactly the same way by creating the main shaft and the heel of the core pin using a sketch and the core feature. These then just need to be joined together to make the finished core pin shapes. It's that simple. Up until now, we've been working solely on splitting the surfaces of the mould up into its constituent parts. To place it into a mould base, we can save the parts we need into a separate assembly. This is just a convenient way of ensuring that all the parts are assembled together in their correct relative locations, but then can also be separated into the correct halves of the mould base assembly as required. Before we do that, let's take a quick look at how we can make electrodes for electrical discharge machining. Small features which are difficult to machine, features which need sharp corners, or features which need a cosmetic finish are manufactured using spark erosion techniques. To create an electrode, all we need to do is sketch out the required shape and then let SolidWorks match the profile of the cavity. Once this is done, we can easily add a spark gap and a further offset to allow for any XY orbital motion that may be available on the EDM machine. The electrode will then be set down in Z by this additional amount. And of course, the electrode remains associative to any changes in the geometry. This mold base was put together from components downloaded from 3D Content Central, an online repository of thousands of standard parts that can be configured and downloaded for free. To change an individual plate, just select what you need from the list of available sizes. If we make all the plates transparent, you can see most of the design work for this tool has been done already, and we just need to place the inserts we created earlier. As this is an automotive part and needs left and right-handed versions, we'll simply mirror the assembly of inserts. SolidWorks is very flexible with assembly structures. Moving parts into their correct sub-assemblies is a very simple drag and drop action. Hiding everything but the inserts helps us see exactly where we're up to. Let's move these two cavity pieces into the fixed half of the mould, and these two core pieces into the moving half. Then move these core pins into the moving half assembly. These side cores into the slide assembly, and this lifter into the lifter assembly. Now everything is accounted for. This lifter does need adjusting and assembling correctly, so first we'll just offset the bottom face so that it extends down. We should really add the connecting detail here, but we can do that later. Next we need to make sure that the lifter mechanism is working correctly by adding a mating condition that will allow the lifter to slide. Now let's see that all in action. When dragging the moving half away, we can see the slides move out along the angle pins. Moving the ejector plate shows the lifters moving correctly, but we only have one ejector pin, so let's address that now. To help locate the pins and trim the ends of them correctly, the split surface from the original design part and the ejector pin location sketch can be inserted here. This determines where the pin should go, making the positioning and copy of the pins very quick and easy. The split surface can then trim the tops of the ejector pins, getting the exact profile required. Since the pins are also needed for the mirrored version of the part on the other side of the mould, we should mirror them around the centre plane. SolidWorks is then able to categorize these into size and shape to help determine if there are any duplicates. If we now go back to the main mould assembly, the pins are all there and we can check that they fit correctly. Finally, we need to consider how this mould will be cooled. On the fixed half, we see that we already have some water lines created in the bolster plate. These can then be continued into the insert, referencing the location of the O-ring recesses using a 3D sketch. A 3D sketch is a convenient way to draw the path of the waterline in all 3 dimensions at the same time. Here we are drawing vertically in the Z-axis and ensuring that both lines remain the same length. A neat way to display the model is to split the window and connect both orthographic views, making it easier to visualize exactly what you are sketching. So now we can adjust the height of the waterline and sketch the remainder of the features at the same time. We'll complete this design by opening the insert in its own window and use library features to add the waterline hole details. This library feature contains configurations for connectors, plugs, O-rings, or just the hole itself, so it's easy to choose what you need when adding the features. These are placed simply by selecting the face to drill and the depth, defined by the 3D sketch we created earlier. All the manufacturing detail regarding hole sizes and tap drill sizes is included in the library feature. Switching back to the assembly, we see that since we mirrored the components, the new waterline feature has been added to the other side of the mold automatically. No tool design is complete without a full set of drawings. Here we have the GA, which could be used for quotation or for detailing the entire assembly. Typical stepped section views show all the detail we've added. The core and cavity detail with ejector pin locations and waterline features. The lifter. The sprue, runner and subgate. And the side core. And of course, a full bill of materials. In an ideal world, the customer would never change their mind. Unfortunately, they do. But fortunately, SolidWorks has a number of tools to alleviate rework caused by drastic changes to the design. SolidWorks utilities can be used to compare geometry between parts and accurately detail the differences between the two. By choosing two revisions of a part, each face is compared and color-coded to give an easy-to-read graphical feedback. This can take a couple of minutes to complete, but the results are worth the wait. Red indicates faces which have changed, and we can see that the main shape of the components has changed significantly. But quite often, not all changes are notified by the customer, so this comparison tool helps us find those small changes like different radii which could have a big impact on the tooling. Our existing design can be updated with the new IGES file, and everything will update automatically, providing the important edges and faces in the new file can be matched with the old. If a change conflicts with the previous design and requires a new parting surface or side core, SolidWorks will indicate any potential errors and try its best to rebuild the mold. Problem areas can then be fixed manually until the mold is working as expected. The good news is that you won't have to start from scratch, even with the toughest of design changes. This change in geometry does not affect the split line or the shut-off surfaces, so we're in good shape to let SolidWorks rebuild the rest of the mold features we made earlier. Finally, let's jump to the final deliverable, the drawing, and see the new core and cavity in place. SolidWorks provides all the tools necessary to take a native or imported part and turn it into a complete mold stack, along with inserts, cores, and a complete fully detailed set of drawings in a very short space of time. Ideal for rapid quotation and fast turnaround. With SolidWorks, you can take advantage of the many enhancements added with each release that provide cutting-edge technology to get your job done faster, reduce time to market, and ultimately design better products.